Hi everyone, this is Bilal. Welcome to tutorial 6. I hope that everything is healthy and good at your site. Well, during the previous tutorials, we have learned about many types of indexing techniques that help with improving the efficiency of the search operations in both relational databases or conventional databases like, okay, 1 second. Gedit, I need a text editor. Relational databases, just like MySQL or Microsoft SQL Server, and the database we have to use during this course, which is Postgres SQL database, and the spatial databases like PostGIS database, which is add-on offered for Postgres database to support spatial data. Okay, we have learned the following indexing techniques: primary index, secondary index, dense index, sparse index, and multi-level index. These were covered during tutorial 1. During tutorial 2, we have learned the B+3, and during tutorial 3 we learned the R3, the region 3, and during tutorial 4 we learned the extendable hashing, linear hashing, and the linear hashing. During tutorial 5 we learned about the multidimensional indices. Okay. We were introduced to 4 multidimensional indices: partitioned hashing, grid index, KD3, and finally bitmap index. Okay, during this tutorial number 6, we will learn about a new data structure or a new indexing technique, which is called the quad trees. Okay, and this will be the last indexing techniques we will learn during this course. So let's start with an introduction to what is quad trees. Okay, so again, we are storing spatial data records in spatial databases like PostGIS, the one we have just mentioned, okay, a few moments ago. We need spatial data structures to support searching using locations as key values. Okay, so the location is represented as a two-dimensional location. Each location has two-dimensional coordinates, x coordinate and y coordinate. Okay, x value and y value. That's why we need spatial data structures to support or to make the search operation more efficient. Okay, and remember, we search inside a spatial database using locations as key values. Okay, here comes the quad trees. The quad trees are composed of nodes. Each node can have up to 4 children. Each one of these children represents different region inside the splitted space or the splitted map, which is represented by the parent node. The whole map is represented by the parent node. Let's explain more about the quad tree. Okay, in binary search tree, the structure of the tree depends on the order of insertions. However, the opposite scenario happens here with the quad trees. The structure of the quad tree is determined only by the values it contains, the values we insert, and the shape of the quad tree is independent of the order of insertions. Remember that each node represents a particular, specific two-dimensional region or section inside the coordinate space or the maps. Internal nodes do not store data. Leaf nodes are the only nodes that store data. Each leaf node holds a single value. Therefore, the coordinate space is divided or splitted or partitioned during insertions more and more and more until each node doesn't contain more than a single point. Okay, let's see few examples of different quad trees to understand the concept, to fully understand the concept. Okay, here is the first example, an example of the basic structure of quad tree that represents a set of points here inside this two-dimensional map. Okay, at first, the root node represents the whole map. The map is divided or split into 4 main quadrants of equal size, which are the following: northwest, this is the northwest quadrant; northeast, this is the northeast quadrant; southwest and southeast. Okay, and they are represented as 4 children of the root node. These are the 4 main children of the root node: northeast, northwest, southwest, southeast. Okay, let's examine and focus on each one of these main 4 quadrants. Okay, let's start with the northwest. The northwest is divided again into 4 subquadrants, and this is reflected by the addition of another level of leaf nodes. These are the leaf nodes. Okay, this is reflected by addition of another level of leaf nodes to the northwest node. Okay, so this is the northwest node, this is the whole quadrant, and it's divided into another level of subquadrants, 4 subquadrants. So we have added them as children, okay, as subnodes under the northwest node. Okay. The last of these aforementioned subquadrants, 1, 2, 3, 4, the last one, number 4, okay, is divided also again into 4 subquadrants of equal size. Also, this is reflected in the quad tree by the addition of another level of leaf nodes. So this is the northwest. This is the children of the northwest, the 4 regions inside the northwest, 1, 2, 3, 4. The last one is divided again into another 4 subquadrants, 1, 2, 3, 4, which are these. Okay. Both the northeast and the southeast quadrants are not divided. That's why they are represented as single leaf nodes inside the quad tree. However, the southwest node is divided into 4 main quadrants as shown in the figure on the right side, and this is reflected in the quad tree itself by adding another level of 4 leaf nodes under the southwest node. So now we understand how the quad tree reflects the what's inside the map, the number of points, the number of regions, the number of sections, the regions that do exist inside another quadrant, regions within region. Okay, so quad tree is very useful for searching inside a very complex map. Just like this, here is another example of a very complex and a very large map. So let's zoom in. As we see As we see, the map is divided or split into many sections in order to isolate each point, okay, of these points. Zoom out again, okay, zoom in, okay. So each node represents one of these boxes, okay, covering that covers some part of the space or the map being indexed. And again, the root node covers the whole area or the whole map, okay. And don't forget, each node can have up to 4 children, okay. Okay. Before diving deep into the details of how to insert and delete into a quad tree, let's see a visualization for a complete quad tree. For a complete example of constructing a quad tree. Here we have a map or a set of points, P. We have a map of 10 points, okay. We need to split this map into 4 main quadrants since it has many points, and we need to isolate these points into separate regions. So we have to divide this map till each quadrant or region contains only 1 point, okay. We have divided the initial map into 4 quadrants: the northwest quadrant, northeast quadrant, southwest quadrant, southeast quadrant. Okay, still we need to divide each quadrant to isolate these points, okay. So for example, we need to divide the northwest quadrant since it has 3 points and we want to separate them. Next, we divide the northeast quadrant to isolate these 2 points. We still have an issue here or a problem here, but we will come later to solve this, okay. Next, we have to divide or split the southwest quadrant as well. However, we don't need to divide or split the southeast quadrant, this quadrant, since it contains only a single point, okay. Next, we have to iterate over these regions that need to be split into 4 subquadrants, like this one inside the northwest quadrant. I mean subquadrant number 4, or the southeast subquadrant inside the northeast quadrant, okay. And also we have to split subquadrant number 3 inside the southwest main quadrant. Note that we need to split this subquadrant again to isolate these 2 points. So let's split this subquadrant just like this. Now we are finished here because every point is located by itself inside a separate region. Here comes the next step. Let's build the corresponding quad tree step by step, okay. So this is the root node. The root node represents the whole area, okay, and this is the first node to be added to our quad tree. The root node has 4 children, which are northwest, northeast, southwest, southeast. So we have added 4 children nodes under the root nodes, okay. Let's loop at each one of these children nodes and add its corresponding subnodes. Okay, so this is the northwest, this is the northeast, this is the southwest, and this is the southeast. Okay, okay, the northwest. Okay, the northwest, let's focus on the northwest quadrant, which is splitted into another level of 4 subquadrants. Let's add them to the quad tree just like this. There is another level of 4 children nodes under the northwest node. These children represent the 4 sections inside the northwest quadrant that exist inside the northwest quadrant. As illustrated in the figure, the northwest quadrant is divided into 4 sections, and they are reflected inside the quad tree. The southeast subquadrant inside the northwest quadrant is divided into another 4 subquadrants, so that each point becomes isolated in a separate region. Okay, and this is reflected inside the quad tree by the addition of another level or another 4 children nodes to the south east subnode of the north under or of the node northwest node. Okay, this is the northwest quadrant. These are the 4 sections inside the northwest quadrant. The last region or the last section is divided into another 4 sections. Here they are. Okay, okay, again, this is the northwest and inside the southeast subquadrant that is located inside the first quadrant, the northwest quadrant of the whole map. Okay, let's stop here. Let's learn how to search inside the quad tree and how to insert and delete nodes into and from the quad tree. Okay, in order to search inside the quad tree, we have to start at the root node. Okay, top-down approach. We are gonna follow top-down approach here and examine each child node and check if it contains or intersects the area being queried for or not. If it does intersect the area we are searching for, we will recurse into that child node whenever we encounter a leaf node. We have to examine each entry to see if it intersects with the query area we are searching for or not, and if it does, we will return this area. Okay, another example for a quad tree that represents the location of certain cities inside North America. You can verify if this quad tree on the right side represents the map on the left side correctly. Okay, okay, true or false. Check if this quad tree represents the map on the left side correctly. Okay, nice. Another example that we will use to illustrate the insertions and deletion operations with the quad trees. Take 2 minutes to check each point if it's inserted in the inside the correct region. Okay, you can check its coordinates, the coordinates of each one of these points. Okay, to check if it's inserted into the correct location or not. This is the whole map, and these are the dimensions of the map. Horizontally from -128 to 128, vertically or on the y-axis from 128 to 128. And these are the main quadrants inside the map, and these are the points. Okay, and as we see, each one of these points does exist inside a separate section or a separate location. Okay, okay, nice and easy. Now let's take a look at how to insert a point inside a quad tree in detail. Just like the search operation, To insert, we will follow the top-down approach, which means we have to start at the root node and determine which quadrant of these subnodes or of its children occupies the point we want to insert, occupies the location of the point we want to insert. Or in other words, which one of these quadrants, okay, the point fits to be inserted inside. Then we will recurse on the node, on that node, and repeat until we find a leaf node. Then we will add the point to the leaf node. So I'm gonna start here. I will check, okay, I have to iterate over all of these children. For example, this one contains the location of the point I want to insert. So I will recurse on its children again to find the suitable section, this section. Okay, the final answer is I have to insert my point inside this section. So we have a situation here. What if the number of points here in this leaf node exceeds the maximum number of points, okay? Then the answer is we have to split this region and move points to the correct subnodes according to its coordinates, okay? We need to see detailed example of this operation to understand it. Okay, inserting point A, okay, will result in the creation of a leaf node holding point A under the root node, okay? Or if the map contains only point A, okay, we have the root node contains point A. Inserting point B causes the dividing of or the splitting of the original map into 4 quadrants to be sure that each point exists inside a separate square or a separate region. So this map is composed of point A and B. So we have to divide the root node or the whole map into 4 main sections, which are the northwest, northeast, southeast, southwest. Okay. Two of these nodes are empty, contains no points, and the other two contains the point A and point B. So we insert point A and point B inside the corresponding quadrants according to its coordinates, okay? Okay. Inserting point C here in this quadrant according to its coordinates doesn't cause any additional splitting of the space because it does exist inside an empty region by itself. On the other hand, inserting point D here will cause the partitioning of the southeast quadrant in order to separate both points B and D, as shown in the following example. So we have inserted point C, and point C, as we see, does exist inside this quadrant by itself, so we don't have to split this quadrant. However, inserting point D inside the same quadrant along with point B, okay, containing point B, will result in splitting this southeast quadrant. So the southeast quadrant is divided into another 4 sections, another level of 4 sections: northwest, northeast, southeast, southwest. And next we assign B and D to their corresponding regions or sections according to their quadrants and the dimensions, their coordinates and the dimensions of each section or each quadrant. Okay. Inserting point E that falls inside the same region containing point A. We need to divide the region, this region, okay? However, after dividing this region, points A and E still lie inside the same subregion. Okay, so we need to divide this region again to separate both points A and E into separate quadrants. So let's visualize. Let's visualize this. Here is the main map divided into 4 sections, and here is point A and here is point E. So this quadrant contains both point A and E, so we have to subdivide it. After splitting the subquadrant, still point A and E, okay, exist inside the same region. So let's divide this region again. And if this case happens again, then we have to partition and split more and more until all points are separated, okay? So inserting point E results in the following quadtree. We have splitted the quadrant that contains both point A and E, and we found that the 2 points are still together. So we have split the subquadrant, the northeast subquadrant of this northeast quadrant again, to isolate point A and E. And remember, we assign the points to their corresponding sections, not rapidly, okay, based on their coordinates and the dimensions of each section. Again, the insertion operation proceeds recursively until the appropriate leaf node is found, and partitioning happens until all points are isolated or separated, okay? A single insertion can add many levels to the relevant quadtree, and this will happen in case of if we have a set of points that are very close to each other. The opposite case is true, okay? Remember that the shape of the quadtree is independent of the order in which data values are inserted. Okay, regarding the deletion operation, deleting a point always involves removing a leaf node. Deleting point A demands removing the node containing it. Since this node contains only point A, removing point A demands removing the whole node and setting this pointer to none or null based on the programming language you are using to implement the quadtree. So let's remove point A. Okay, now as we have just said, we have to set the parent's pointer to null and remove the leaf nodes containing point A from the quadtree. Okay, now let's see the case of deleting a leaf node which may cause its parent to underflow or disappear. Okay, let's delete point B. Now, after deleting point B, the parent, this node, contains only a single point, only point D. And hence, there is no reason that it must be splitted or partitioned into 4 sections. So we can contract this branch by replacing this parent node with the remaining leaf child node. Okay, again. After deleting point B, this area or this section now contains only point D. So there is no meaning, okay, for splitting this area into 4 sections. It has only a single point D. So let's remove this splitted node and replace it with point D inside the southeast quadrant of the whole map. Okay. Contracting the branch results in the following tree. Note that if the root node of this tree didn't have another child, okay, imagine that there is no node C here, the branch contraction could continue. Okay, we can remove more levels or more nodes. Okay, if a data point that is inserted lies very close to another data point in the tree, many levels of partitioning may be required to separate them. The minimum height of the quad tree is calculated by the following mathematical rules. Achilles heel, which is the seal, okay, rounding up, logarithm of the following fraction, square root 2 times s over d, all inside the logarithm. Okay, so what is s? S is the length of the side of the whole world, of the whole map, and d is the minimum distance between any two data points in the tree. So for example, here is the map, and we don't have a quad tree yet. We have inserted point C, and we want to determine, okay, roughly how many levels will be added to insert point C. What is the minimum height of the quad tree after inserting point C? So we can use Achilles heel rule. Okay, given the distance d between B and C, and s the length of the whole map, using this rule we can compute the minimum height of the quad tree. The problem, now let's solve the problem of a very lengthy quad tree branches. Okay, the problem of a lengthy quad tree branches can be solved by allowing each leaf node to store more than one point, making the leaf node a bucket. This complicates the implementation of the tree, but reduces the cost of the search operations, since the branches of the tree would be short. And this is the main goal of the advanced database techniques, to make the search operation more efficient. If buckets are used, then the minimum height of the quad tree can be computed using the same Achilles heel rule, the mathematical formula explained in the previous slide. Okay, but however, these the variable, the unknown variable d, represents different concepts in this case. Okay, please look very carefully for fine details. D here represents the minimum side of the square or the region that contains more data elements than a bucket can hold. So let's visualize it. So this is our map, and imagine that here do exist 4 points, and the maximum size for the bucket, the maximum allowed number of points is 4. We want to insert point number 5 here, so we can compute the minimum number, or the minimum height of the quad tree after inserting this point using Achilles heel. However, d here represents the length of the square that contains more data points than allowed, than the number of points, the allowed number of points. Okay, and s represents the length of the side of the whole map. So d in this case doesn't represent the minimum distance between any data points. Okay, again, it represents the minimum side of the square that contains more data elements than a bucket can hold. Finally, let's build a quad tree from scratch given a set of points. To fully understand how quad trees work, okay? Before we start this example, let's remember that the order of insertion doesn't change the quad tree, Since we insert points, each one has the same location on the map. So it doesn't matter if we insert these points in different order. It doesn't matter if we started with F or G or A, or if we inserted them sequentially or in the opposite order of, or in any order, okay? All of them lead to the same final map and the same final quadtree. We have these points to insert one by one: A, B, C, D, E, F, G, H, J, K, L, M, N, P. And we have the coordinates of each one of these points. Here's our map, and it has the following dimensions. On horizontal level from negative 128 to 128, and on vertical level from negative 128 to 128. Okay, so let's insert these points one by one. Let's start with point A. Point A has the following coordinates: 100 and 125. So starting from the origin 100 and the origin of the y-axis 125, I think point A should be here. This is point A. Okay, now we don't have to split the map or divide the map into 4 quadrants, since it has only a single point. Okay, let's insert the next point, point B. Point B has the following coordinates: 25 and negative 30. 25 and negative 30. Starting from the origin of the x-axis, 25 should be here. Starting from the origin of the y-axis, negative 30 should be here. So point B should be here. Okay, here is point B. Now the whole map contains more than a single point. It contains 2 points. So we have to split the map. Okay, in this case, the situation, we have to split the map into 4 quadrants of equal size. Okay, this is the map after dividing it into 4 main quadrants: the northwest quadrant, the northeast quadrant, the southwest quadrant, and the southeast quadrant. Okay, now point A and B are isolated. Point A does exist inside this quadrant, and point B exists inside a separate quadrant. This is the northeast quadrant, and this is the southeast quadrant. Next, let's insert point C. Point C lies at negative 55. So starting from the origin of the x-axis, negative 55 should be here. And 80, starting from the y-axis, 80 should be here. Okay, so C lies inside the northwest quadrant, just like this. And we don't need to split the map or any of these quadrants, since each one of these 3 points exists by itself inside a separate region or a separate section. Okay, so we don't have to split the map right now. Maybe later in the near future we will split it many times, but for now we don't have to split the map. Okay, let's insert point D. Next, point D. Point D lies at 125 horizontally and negative 60 vertically. So point D shares the same quadrant with point B. So we have to split this quadrant, the southeast quadrant, like this. Let's proceed. Okay, let's proceed. Before we proceed, now point B and D are isolated from each other. Okay, and C and A are also isolated in separate quadrants. So let's insert the next point, point E. Point E has the following coordinates: 80 and 80. 80 and 80. 80 and 80. So point E should be here. Okay, as we see in the following figure, point E and point A shares the same northeast quadrant. So we have to split this quadrant. We have to split this quadrant into 4 sub-quadrants of equal size, okay? After splitting the quadrant, we still have a situation here. Still points E and A exist inside the same region. So we have to split this sub-region again until the 2 points are isolated from each other. Yes. Now we have succeeded to isolate points E and A. Next comes point F. Okay, F lies at negative 80 and negative 8. Negative 80 starting from this origin, going left, negative 80, and starting from the y-axis, negative 8. F should be here. F does exist inside the southwest quadrant by itself. So in this case, we don't need to split anything. We don't need to split anything. Okay. Next comes point G. Point G lies at negative 12, a little to the left of the the x-axis origin, and negative 112. Negative 112. So G should be here. F and G shares the same quadrant, which is the southwest quadrant. So we have to split this quadrant. So we can see that F and G shares the southwest quadrant. So we have to split this southwest quadrant to separate F and G. Yes, just like this. Okay. Again, now each point is located inside a separate region or a separate quadrant, so we don't have to split furthermore. Okay. Next, point H, and before inserting H, we can see that G and H, okay, lie at the same or on the same y-axis, okay, negative 112. So they have the same y coordinate. They lie on the same line, a horizontal line. So H should be here beside G. So G and H, yes, G and H shares the same subregion. So we have to separate this subregion to isolate them. We have to divide it into 4 subquadrants of equal size, just like this. Now let's insert point J, and we are lucky because point J lies inside a separate region, okay, which is this section by itself, so we don't have to split any of these regions. Next, point K. Point K has the following coordinates: 60 and 100. 60 and 100. 60 should be here. 100 starting from the y-axis origin. 100 should be here. So J and K, as we see, shares the same quadrant, which we have to split. Okay, which we have. This is point K and point J. We have to split this quadrant to isolate each point inside a separate region, just like this. Next, point L. Next, point L. L has the following coordinates: 48 and 48. 48 and 48. 48 starting from the origin of the x-axis should be here, and going up starting from the origin of the y-axis, L should be here in this quadrant. Now L lies in this quadrant or subregion by itself, so we don't have to split any part of this map. Next comes point M. M lies at 36 and 8. 36 should be a little before L, horizontally, and 8 a little above the y-axis. So M should be here. M and L shares the same region. Yes, M and L share the same region. So we have to split this region into 4 subregions. Yes, just like this, in order to separate points L and M. Let's insert point N, 4 and 60. 4 should be here, a little to the right of the x-axis, and 60 starting from the y-axis. N should be here, okay? So N is located by itself inside a small subregion. Finally, let's insert point P. P lies at 28 and 30. 28 and 30, I think P should be here in this empty subregion. So this is the final version of the map, the final shape of the map. We are finished here. We have inserted all of the points, and I think that each point, I'm sure that each point is isolated inside a separate region. So the final thing to do in this tutorial is to build the corresponding quadtree to this relevant map. So let's zoom in. Let's take a screenshot of this final map. Again, the painting software, file, open the screenshot, bring it to the left, sorry, let's zoom in a little. So this is the map, okay, and this is the brush. Okay, here is the root node. The root node represents the whole map. Okay, the whole map. Okay, the whole map, the map is divided into main 4 quadrants: north, west, northeast, south, west, southeast. So this is the northwest, and this is the northeast. This is the southwest, and this is the southeast. Okay, let's focus on the northwest. Northwest contains only a single point C. We have a leaf node, so we have a leaf node here. Okay, contains point C, containing point C. Next, the northeast. The northeast is divided into another level of 4 subquadrants. So 1, 2, 3, 4. The first 3 subquadrants is each one of these first 3 subquadrants is divided into another 4 subregions. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And last one is an empty quadrant. Okay, this is the first subquadrant. It has 4 subregions: empty, K, J, empty. So empty, K, okay, this is K, and this is J, empty. The second quadrant, sorry, or subquadrant, contains empty, A, E, empty. Empty, A, E, empty. And the third one contains the following points: N, L, B, M. N, L, P, M. So this is the northeast quadrant. This whole area is the northeast quadrant, and it's divided into 4 main subquadrants. 1, 2, 3, 4. The first one is divided into 4 main sections. 1, 2, 3, 4. Empty, K, J, empty. Empty, K, J, empty. Second one is divided into 4 main regions. Empty, A, E, empty. Empty, A, E, empty. The fourth one is divided into 4 main regions. NLBM, NLBM. And the fourth one, sorry, this is the third one. The fourth one is empty, okay? It is not divided or splitted, and it has 0 points. That's why we have inserted this empty leaf node. Okay, now let's move to the southwest quadrant. The southwest quadrant is divided into 4 main 1, 2, 3, 4 main subquadrants. So 1, 2, 3, 4. The first one, this one, contains point F, only point F. So let's insert a leaf node here, contains point F. Second one is empty. The third one is empty. And the fourth one is divided into 4 subregions, just like these, okay? So 1, 2, 3, 4. Let's add another level of nodes. Empty, empty, HG. Empty, empty, HG. Okay, let's move to the fourth quadrant, this one. The fourth quadrant. The fourth quadrant is divided into 4 main subquadrants. The first 2 contain B and D, and the last 2 are empty. So empty leaf node, and here an empty leaf node. This is the final quadtree. This is the root node. These are the main 4 quadrants. 1, 2, 3, 4. The first one has only point C. This is the first one. The second one is divided into 4 subquadrants. 1, 2, 3, 4. 1, 2, 3, 4. The first one is divided into 4 subquadrants or subregions. 1, 2, 3, 4. Empty, K, J, empty. Second one is divided into 4 subregions. Third one is divided into 4 subregions. The fourth one is empty, and so on. Okay, so this is the final answer. So during this tutorial, okay, let's summarize what we have learned today. During this tutorial, you have learned about the quadtree. Why do we need the quadtree? What is the quadtree? How to construct the quadtree? How to split a region? How to draw the map? How to insert a set of points into a map and the corresponding quadtree? The Achilles heel rule, mathematical rule, to compute the minimum height of the quadtree. And we have seen a few examples, okay, of different quadtrees. Okay, so I think we are finished here in this tutorial. Study well, stay healthy, stay safe, and I hope that you have enjoyed watching this tutorial. And I guess I have to say goodbye. So goodbye, everyone.